All right, before we go on to this next example, let's just stop and take a look at the general form of an exponential function. So we can write an exponential function in one of these two ways, where q is equal to some a value times 1 plus r to the t, or if 1 plus r is equal to b, we can also write it as q is equal to a b to the t. Now this t is only applied to b, right? So it's only b that's being raised to the power, and then we're going to multiply by a. All right, so a is the initial quantity, right? So if t is equal to 0, right, q of 0 would just be a b to the 0, and b to the 0 is 1, right? So this is just equal to a. Right, so the a value is our initial value of the quantity that we're looking at. B, which is 1 plus r, is called the growth factor. Okay, so it's the factor that we're multiplying over and over by, right? That's the thing that we're raised to the t power. And then r is the growth rate. Now we saw a couple of different types of growth in the last few examples. In the first two examples, we saw examples of exponential growth, right? So we had the value of the CD was growing over time, right? And then we had the tribble population. The population was growing over time. So our r value was positive. And so if the r value is positive, that means b is greater than 1, and we have exponential growth. All right, so the value is increasing, or the quantity, or whatever it is increasing over time. It's an increasing function. If r is negative, now we saw an example of this with the caffeine, right? Because the caffeine was being eliminated, and we saw exponential decay. So when r is negative, then b is between 0 and 1, right? So I think in that caffeine problem, we had a growth factor of 84% because 16% of the caffeine was being eliminated every hour. So we had a value, a growth factor of 0.84 or 84%. And if that's the case, then we have exponential decay. So our growth rate is not really growth; it's negative, right? So it's decreasing, and if you take away the negative, that would give you the percent decrease each time. All right. All right. So let's take a look at this next example. It's kind of a long one, so you have to bear with me here. All right, we're just going to let me actually have both of these on the screen at the same time, at least initially. All right, so in this example, we've got some equations, some exponential functions, and we want to give the initial value, the growth factor, which is b, and the growth rate for each one, and then state whether the function represents exponential growth or decay. So now these first two are pretty straightforward. Now we can just look at, we can compare this exponential function with the standard form, and we can find those values that we're looking for. So you can see this is a, and this is b, and so I can say that a is equal to 14. That's our initial quantity when t equals 0. B is equal to 1.05, right? And then R, so B is equal to 1 plus R, which means that R is equal to, if I just subtract 1 from both sides, it's B minus 1, right? So B minus 1 is just 0.05, right? So we have a positive growth rate, or we could write it as 5%. Oftentimes these growth rates are given as a percentage. All right, so R is positive, which means that we have exponential growth. Exponential growth. All right, for this next one, again, it's pretty straightforward. We can compare it to the standard form, and we can see that this is our A value and this is our B value. And so A is equal to 120, and B is, our growth factor is 0.86. Now our growth rate is B minus 1. So if we subtract 1, so it's going to be, I'll just write that out, 0.86 minus 1 is a negative 0.14. Or I could say 14%. Okay, or negative 14%, right? Because it's negative. All right, so our growth rate is a negative 14%. So it's actually not growing. it's the opposite of growing. It's decaying. So this is exponential. Oops. Exponential decay. So in this case, we're starting out with 120, and the amount is 86% of what it was in the previous time period each time. All right. Now these other ones are a little complicated. You got to remember how exponents work. So they're not in the standard form, and we have to put them in standard form. So let's take a look at this first one. We have q is equal to 2 to the t plus 5. All right. Now we need it to be in, I'll just write it. We need q equals ab to the t. Just t, not t plus 5. We just need t. So let's use the properties of exponents, and I can write that as 2 to the t times 2 to the 5. All right. Remember that sum becomes a, we can break it up like this into a product. Okay, because of the fact that when we multiply values with the same base, then we can add the exponents. So we're just going backwards. And 2 to the 5 is 32. So I'm going to put that out front. So we have 32 times 2 to the t. All right, so now we have just something raised to the t power. So now I can see that b is 2. And a has to be 32. So a is equal to 32. B is equal to 2, and remember that R is equal to B minus 1, so R is equal to 1, which is essentially saying we're getting 100% growth each time, which makes sense because it's doubling, right, every time period. So this is exponential growth. All right. So again, now we have to rewrite this next one. We have 3 to the minus t. All right, now we don't want t, we don't want minus t, we want t. So let's break this up into 60 times 3 to the minus 1 to the t, right? So this, we have basically a product of powers here, right? We have minus 1 times t, so I can write this as power to a power. All right, and 3 to the minus 1 is just 1/3. Now we have it in the right form, and we can see that a is equal to 60, b is 1/3, and so then r is equal to 1/3 minus 1, or 3/3, which is a negative 2/3. So, or we could write it as approximately a negative 67%, right? If we round it off. So our r is negative 2/3. And so our growth rate is negative, so we don't have growth, we have decay. So exponential decay. Alrighty. Got a couple more. They get a little tricky. You just need to remember how exponents work, and that's the key. All right, so here, again, we have, we get 8 to the t over 3. Right, we want something to the t, not t over 3. So we got to get rid of that over 3 part, right? So I can rewrite this as 8 to the 1/3 to the t, right? Because 1/3 times t is t over 3. All right, so I'm just breaking this into a product and taking a power to a power. And and I know that 8 to the 1/3, that's just the cube root. So the cube root of 8 is 2. So this is just 2 to the t. So that's pretty simple. That's just the same thing as 2 to the t. And now, okay, so what is a? So I can always write this as 1 times 2 to the t. So a is actually 1. And if you're not sure, just put t equals 0 in, right? If t is equal to 0, 2 to the 0 is 1, so the initial quantity is 1. B, the growth factor is 2. R is equal to B minus 1, which is 1. So, or we could write it as 100%. It's 100% increase. So this is again exponential growth. All right. All right. Let's take a look at this next one. We got a lot of stuff going on here. So again, it's just a matter of remembering the properties of exponents and rewriting this in the standard form. So I'm going to rewrite this as, let's see, I've got a third in there. This really 2, so we have 8 to the 2t, or 2 minus t over 3, right? Now that's the same as 1/3 times 2 minus t. So I can do something similar to what I did before. I can write 5 times 8 to the 1/3 to the 2 minus t. And I know 8 to the 1/3 is 2, right? Because that's the cube root. All right, so let me just do that. 5 and then times 2 to the 2 minus t. All right, so now I have basically 2 plus a negative t, right? So I can break that up into 5 times 2 to the 2 times 2 to the minus t. That's supposed to be minus t. That minus got lost. T. All right, minus t. All right, you see how I did that? I just basically have a sum. It's plus a negative, but it's a sum. So I break it into the product of 2 squared times 2 to the negative t. It's the same thing, right? Because I have a common base. And now I know 2 squared is 4, right? So this becomes 20. And then I can do the similar thing to what I did in part D here, and I can write 2 to the negative 1, 2 to the minus 1 to the t, right, to get rid of that negative t. And 2 to the minus 1 is a half, right? So I have 20 times 1/2 to the t. So now I have it written in the standard form, and then I can read off that A is equal to 20, B is equal to 1/2, so R is equal to 1 minus, or say 1/2 minus 1, right? 1/2 minus 1, which is a negative 1/2, or 50%, a negative 50%. So it's decaying by 50% each time. So the R is negative, so we have exponential decay. Alrighty, we have one more example, and I will see you there.